All right. Day 3, warm up. The first question asks us to estimate, and again, it's very important that we pay attention to what function they're asking for. On this one, they're asking for us to estimate the derivative, but the function we know is t of x, and they're asking us to estimate t prime of x from a table of data. This takes us back to first semester. We did this frequently with our average rate of change formula, and we pay attention to, we're supposed to be looking at a x value of 7 centimeters, which would fall right here between 6 and 8. And so that is how I knew to pick these two. They sandwich the value they're asking me to estimate the rate of change at. And so then we use our average rate of change formula to find the slope of that secant line that would run across the x value of 7. And so what we're looking at is t of 8 minus t of 6 over 8 minus 6. And we get those values from our table. So 55 minus 62 over 2, which gives us a average rate of change of negative 3.5. And then again, we can look at our labeling from how each of these functions would be labeled in the table. So t is labeled in degrees Celsius, our x is labeled in centimeters, and so that's how I would label this, is degrees Celsius per centimeter. Question 2 says write an integral expression for in terms of t of x for the average temperature of the wire. So when it asks us for the average of a function, which is what we have, the average, and we have the temperature function, that always comes from 1 over b minus a. And in this case, our b and a would come from the ends of our integral. So here's from a to b of our interval. So 1 over 8 minus 0, the integral of 0 to 8 of the function they're asking us to find the average of, so of t of x dx. That would be the integral expression. Estimating that using a trapezoidal sum would look like the following. So we've got that 1/8 from the average part of it, and then the trapezoidal sum, we would have, again, each of our trapezoids have to be separate because the heights are all different. So 1/2 times our height of 1, base 1 plus base 2. And move on to the next trapezoid that has a height of 4. I'm getting my heights from the difference between the x values. So the difference between 1 and 5 gives me the height that I just wrote here. The two bases come from the function values at 1 and 5. And the next one has a height of between 5 and 6. So height of 1, function values at 7 and 6 are the bases. And our last one, the height between 6 and 8 would be 2, bases of 62 and 55. Multiply all that out and we would end up with 75.688. And it is degrees Celsius, and so it does say indicate units of measure. So I want to come back over here. That first fraction is 1 over units that are in centimeters. Inside our integral, the t of x is in degrees Celsius and dx is indicating centimeters. And so if we were to multiply those three things together, the centimeters in the bottom here would cancel with the centimeters in the top here, leaving us with just degrees Celsius, which you see as our label over here. All right, the next one, we are asked to evaluate an integral. Now remember, we have multiple methods for evaluating an integral. One of those would be, can I look at the picture of this function, t prime of x, and find a geometric shape under that curve from 0 to 8? Well, we don't know what that picture looks like. Another option would be if I knew the function t prime of x, that I could go type it in my calculator and do math 9. We don't know what the function t prime of x is, so I can't do that. And another option for evaluating an integral. So when you're asked to evaluate an integral, these are kind of the things that I would like think through in my mind. Which of these options do I have? Can I do an approximation using rectangles or trapezoids? Typically, if that's the route I'm going to go, they would have told me that like they did above where it said use a trapezoidal sum. But again, I don't know anything about T of X. And so I can't go do that trapezoidal or rectangular sums or anything. But our last option that we haven't talked about yet for evaluating an integral is using the fundamental theorem of calculus part 2 that says you can use antiderivatives to evaluate your integral. And so we look closer again at the function inside of here is t prime of x. Well, the antiderivative of t prime would be t of x. And so our fundamental theorem of calculus says that then the integral from 0 to 8 of t prime of x dx will equal its antiderivative, t, evaluated at 8 minus t evaluated at 0. And again, those are just values that we can go get in the table above. T of 8 is 55. T of 0 is 100. And 55 minus 100 is negative 45 degrees Celsius. It does say explain the meaning of that integral, and the meaning of that integral is how much the temperature will change from 0 to 8 centimeters. So we would say that the temperature is going to decrease 45 degrees Celsius on the lengths from 0 to 8 centimeters. The total amount of degrees that will decrease over that amount of distance. Okay, in our next one, if we kind of relate integrals to area and in which direction are we moving, first of all, in this picture over here, we would see that we have several different shapes. And I'm going to talk about these in terms of just area, which means talking positive right now. Our first shape, if I connect my function to the x-axis, would be that triangle up there, and that triangle would have an area. Let's see, its base is 1, 2, 3, height of 3. 3 times 3 is 9, half of 9, so that we're looking at an area of 4.5. And then our next one would, again, if I connect the function to the x-axis, would be the shape of a triangle again. As we look at this one, it's got a base of 1, 2, 3, height of 2, and I'm just doing everything positive right now, just talking what area are we seeing in these different sections, and that would give me an area of 3. And finally here, we've got an area of a semicircle. So semicircle means half. Area formula for a circle, pi r squared. The r on this, if we go from our middle out, would be 2, which means the area on this one we're looking at would be half of 4 is 2 pi. Okay, and then we look at our anchor point, and our anchor point is going to be the information they give us, and I'm just going to use that as kind of where to start our conversation. And we're going to do these a little out of order just for ease, but the anchor point they give us is that f of 1 is -3, meaning our function that they're asking about in each of these questions at x equals 1 has a value of 3. So that's kind of our starting point right here. So they're at x equals 1, so this little barrier right here, our function currently equals -3. As we move forward, it would be like we are, and actually let me show you this in a little bit more calculus way. And so just to kind of prove my point here about moving forward and moving backwards, if I want, we actually saw a question like this. If I wanted a function that had this property, that f of 1 equals -3, that I could create the integral And we strategically went from 1 to x because 1 was the value they were evaluating f at in the initial conditions of f prime, which is the picture we're looking at, of t dt. And then we did minus 3 so that when I evaluated this function at 1, this part would be 0 because it would go from 1 to 1. Minus 3 would give us a value f of 1 equals negative 3. Okay, so utilizing that fact, if I were to say, okay, what is f of 4? And I just follow my calculus here now that I've created that, f of 4 would mean I would be plugging a 4 in here. Minus 3. Well, this section right here would be the area under the curve, but because that area is this part right here, that would be the area that you see in this picture that goes from 1 to 4. It's below our x-axis. When we are talking an integral, below our x-axis is negative. So we'd say this part would evaluate to negative 3. And then the minus 3 from how we had created this function means that f of 4 would equal negative 6. And so what happens is, as you're moving from our anchor point, if you move from there to the right, things are as we see. So above would be added to negative 3. If our area that we see in that section is below, we would subtract that from our negative 3, as we did as we moved from 1 to 4 to get f of 4. We took negative 3 minus 3, and we got an answer of negative 6. So continuing that idea, again, for f of 8, if I do it not so much in the integral format, but as we look at it, just kind of adding and subtracting areas in that way. So I start with my anchor value at f of 1 being negative 3. I subtract area below the x-axis, so I would subtract the 3 area that you see from 1 to 4. And then area that is above my x-axis, I would add, which would be the 2 pi. For this semicircle, and that would get me all the way from 1 out to 8, which would evaluate for f of 8, giving us a total of negative 6 plus 2 pi. Okay. So then the last part of it is that f of negative 2. And basically, again, I can go back to the calculus way of doing this, and that is if I were to look at the integral, or just plugging it into the function that I had written, my integral would go from 1 to negative 2. And we don't want to integrate backwards. And so the first thing that we would do is we would deal with this by flipping and going from negative 2 to 1, and that would move that negative out front. We can always flip the order of integration by putting a negative out front. And then this section right here is represented by that triangle, and we found its area to be 4.5. But this negative needs to now sit in front of it. And so then if we put that all together, we find out that f of negative 2 is negative 4.5 minus 3, or negative 7.5. Okay, and so what happens is, from where our anchor point is, if we move in the opposite direction of how we normally integrate, we think opposite, meaning if area is below my x-axis, that is what I would actually add to my anchor value. And if area is above my x-axis, I would subtract it from my anchor value. Because you're integrating backwards, And so you would think opposite of what you see. And then think of it in a different direction. Now I know that the value of my function at -2 is -7.5. Moving from this point, let me get a different color here so you can actually see what I'm doing. Moving from that point right there over to f of 1, I add 4.5 area above my x-axis, landing then at an answer of -3, and -7.5 plus the 4.5 above does get me to -3. So you can see that if we start all the way back at -2 and integrate in the direction we are used to, from left to right, that this all does work together. All right, moving to the back side, we are looking at some implicit differentiation, which we haven't done for a while. And so our implicit differentiation, just remember, be cautious if we have products. Let me get a color we can see a little better here. If we're looking at a product here, like we are here, make sure that you think through your product rule. So it'd be r first times the derivative of the second, and that would be 2y. And then always, anytime we take the derivative of a y, we follow it up with a y prime plus the second times the derivative of the first. Well, the derivative of x is 1. And then we repeat that same thing for this second function, negative, and I'm going to consider it -x cubed plus y. So I would say the first, which would be -x cubed, times the derivative of the second, which would be y prime, plus the second, y, times the derivative of the first, which would be -3x squared. And then this equals, and our derivative of 6 is going to be 0. Okay, so from here, we need to find anything that has a y prime. We've got a y prime here, and we've got a y prime here, and we want to get those onto the same side by themselves. Oops, I should get all the way to that. So this 2xy y prime is going to stay on this side, and the -x cubed y prime will stay on this side. Anything that does not have a y prime, which we'd be looking at here and here, we're going to move to the other side of the equation. So I'm going to add the 3x squared y and subtract the y squared to move it to the other side. And then we come back over here and we factor out our GCF of y prime. And finally divide by that 2xy minus x cubed on both sides. And we end up with y prime equals 3x squared y minus y squared over 2xy minus x cubed. And you are welcome to leave it as y prime. I had a couple questions about that. Y prime and y dx are the same thing, and welcome to leave. Okay, so that was part A, implicit differentiation to get to dy dx. Part B says find all, that's an indication that we may have more than one, right? Find all points on the curve whose x coordinate is 1. So remember, these are going to be points where when I do this, the x coordinate is 1, okay? And write the equation for those lines at the tangent. So if I go back up to my equation, the point comes from the function itself, and x is supposed to equal 1. Okay, well, if I put a 1 in for all of the x's, I can then solve for what the y would be if x is 1. So it looks like we have a quadratic here, so I'm going to get it equal to 0, factor, and it turns out we actually get 2 places on our y-axis when x equals 1. And so we end up with 2 points, which means we'll have 2 lines because we have a line through each of those. We have one point where it is 1, 3, and a second point where it is 1, -2. So then the slope for each of those is slightly different based on the curve itself. So let's start with the 1, 3. To write the equation, we now need to know its slope at 1, 3, and remember that the slope comes from the derivative, and we already did that work. So I bring down my derivative. And we evaluate it at the specific point, 1, 3, which means everywhere there is an x, I'm going to plug in a 1. Everywhere there is a y, I'm going to plug in a 3. And this is going to be the slope of the tangent line at 1, 3. So let's see what we get. Okay, well, in the top, I end up with 3 times 3 is 9, minus 9 is 0. And in the bottom, I get 6 minus 1 is 5. Well, that gives me a slope of 0. Just some algebra reminders, a slope of 0 is a horizontal line. A horizontal line is always y equals a number, and it must be the y equals that goes through this point. And so that is why my equation for this particular one would be y equals 3. So then we repeat this process with the other point that was given to us, and the other point, or not given to us, that we found. The other point we found is 1, negative 2. So now I go find the slope at 1, negative 2, doing the same process. So taking my derivative from above, evaluating it at 1, negative 2. Okay, and this time, let's see, we get negative 6 minus 4 would be negative 10. Negative 4 minus 1 would be negative 5. Negative 10 over negative 5 would be 2. So we get a slope of 2. So then our equation, we actually will have a more normal looking equation on this one, would be y minus our y value, so y minus negative 2 over our slope of 2, equals our slope of 2, x minus 1. Again, I can't stress enough, when you're writing your equation, always the same process. Point comes from the equation, slope comes from the derivative, and that when it says all points, that's a good indication that you're going to get more than one. Go plug the information they give you into the original function, right? Because that's where our point comes from, to find the other part of the point. All right. Finally, this one got a little ugly, but it says find the x coordinate of each point of the curve where the tangent line is vertical. And so remember, the tangent line means we would be talking the slope. And vertical means that our slope of our line needs to be undefined. Well, undefined means that we would be looking at some number over 0. That's when we say that something is undefined when talking a slope. So if we consider our slope from above, our derivative, I'll bring that down so we can see it. Of this, in this particular problem, because it's supposed to be vertical, which means undefined, that means that our denominator, 2xy minus x cubed, needs to equal 0. Now, just as a side note, what if they had said if it was horizontal instead of vertical? Horizontal means that our numerator, 3x squared y minus y squared, would have needed to equal 0, because that's how a fraction equals 0, and horizontal is when your slope equals 0, not undefined. So we could change the question to horizontal instead of vertical, and that would change which part of our derivative we would have set equal to 0. But it was vertical, so we set our denominator equal to 0. Now, what we are looking at currently, and again, find the x coordinate of the point on the curve. So eventually this is going to come from the equation itself. And I'm looking at right now something that has two variables in it, the best I can do is solve for one of those and do a system of equations via substitution or elimination. This looks like it's more set up for a substitution type of problem. And I only have one y value right here, so I would decide to solve for y on this. And my x's do simplify there. I can take an x out of the top and bottom, and we end up with x squared over 2. Okay, so now what I need to do is I need to go get the function from above, which was xy squared minus x cubed y equals 6. And what we're going to do is we are going to sub in. So I just found out that y will equal x squared over 2. And so I can take out every y up here and replace it with an x squared over 2. And so I rewrite this equation. And instead of all the y's, I'm going to put in an x squared over 2. Oops, I see I forgot a squared on that y right there. And now I have this equation right here is one equation with one variable in it, which means I can solve for that variable, which is the variable they were asking for, the x coordinates, and I have it written in terms of x. So now we just need to do the algebra to simplify this. So I'm going to square this. Make this look like a fraction and multiply straight across the top, straight across the bottom. And then same thing here, multiply straight across the top, straight across the bottom. Okay, trying to show all my steps of algebra here so we can follow. I also need to get this to have a common denominator so that I can add those two fractions together. Which would give me a negative x to the 5th over 4 equals 6. Multiply by 4. Divide by a negative 1. And now 5th root. And we end up with the very ugly answer of the 5th root of negative 24.